The Friedel-Crafts Alkylation is an electrophilic aromatic substitution, or EAS reaction. In EAS reactions, a proton on an aromatic ring is replaced by a potent electrophile. And in all EAS reactions, the aromatic ring acts as a nucleophile. Specifically, in Friedel-Crafts alkylation, an alkyl group is installed on the ring. The reaction requires an alkyl chloride and aluminum trichloride, and it produces an alkyl benzene. The transformation begins with a Lewis acid-base reaction between the alkyl chloride and aluminum trichloride, which acts as an electron pair acceptor, thereby making it a Lewis acid. A Lewis acid-base complex results. What happens next actually depends on the structure of the alkyl chloride. When the alkyl chloride is secondary or tertiary, aluminum tetrachloride dissociates and a carbocation forms. Here we have both secondary and tertiary carbocations being formed from the dissociation occurring with secondary and tertiary alkyl chloride substrates. However, when the alkyl chloride is primary, dissociation would lead to a high-energy primary carbocation, so it does not occur. The primary carbon is nevertheless electrophilic because it bears a partial positive charge. A pi bond of the nucleophilic aromatic ring then attacks the electrophile to afford a sigma complex. When the alkyl chloride is secondary or tertiary, the electrophile is a carbocation, and a tertiary carbocation has been shown here. A sigma complex results from this attack. The sigma complex is named as such because it possesses the new blue sigma bond. It also has a carbocation, which is delocalized to 3 positions on the ring through resonance. Finally, the loss of a proton from the only ring carbon that is sp3 hybridized restores aromaticity to the ring and produces the product. In this reaction, it is a chloride that dissociates from aluminum tetrachloride that actually removes the proton. And in this fashion, HCl is produced as a byproduct, and the aluminum trichloride catalyst is regenerated. The alkyl benzene is the primary reaction product. When the alkyl chloride is primary, the electrophile for the EAS reaction is the Lewis acid-base complex instead of a carbocation. A pi bond of the aromatic ring attacks the partially positive carbon of the Lewis acid-base complex and displaces aluminum tetrachloride. This results in the formation of a sigma complex as expected, and the intermediate sigma complex is converted to product through loss of a proton, as shown previously. Now let's turn our attention to some specific examples. For instance, benzene can be treated with isopropyl chloride, a secondary alkyl chloride, and aluminum trichloride to provide isopropyl benzene. The conversion begins with Lewis acid-base complex formation as a lone pair of electrons from the chlorine attacks the aluminum trichloride to produce this complex. Since the center bearing the leaving group is secondary and would therefore make a reasonably stable carbocation, aluminum tetrachloride dissociates to afford that carbocation. And it is the isopropyl carbocation that acts as the potent electrophile inciting the attack of benzene, which results in the formation of a sigma complex. As the red pi-bonding electrons shift over one bond, the carbocation is delocalized to a second position on the ring, and when the green pi-bonding electrons shift over one bond as well, the carbocation is delocalized to a third position on the ring. And the mechanism concludes with the loss of a proton from the only sp3 hybridized ring carbon, which restores aromaticity to the ring, affording isopropyl benzene as the reaction product. In this new example, ethyl chloride, a primary alkyl chloride, is used as the reagent, and this alters the mechanism slightly. The Lewis acid-base complex forms as expected. However, in this case, dissociation of aluminum tetrachloride would yield a highly unstable primary carbocation. Therefore, no dissociation ensues, and the Lewis acid-base complex itself will act as the electrophile in the next step of the mechanism. Benzene attacks that electrophilic primary center directly, actively displacing aluminum tetrachloride, and the expected sigma complex results. This sigma complex has the same type of resonance delocalization that we've seen in previous examples. The reaction concludes when chloride dissociates from aluminum tetrachloride and removes a proton from the only sp3 hybridized ring carbon. This restores aromaticity to the ring and provides ethyl benzene as the product. Now let's consider some examples with regiochemical implications. For instance, phenyl acetate can be treated with tert-butyl chloride and aluminum trichloride to produce the para-substituted compound as the major product and the ortho isomer as a minor product. The reaction is initiated by the formation of a Lewis acid-base complex. And since tert-butyl chloride is a tertiary alkyl chloride, dissociation of aluminum tetrachloride occurs, resulting in the formation of a reasonably stable tertiary carbocation. The tert-butyl carbocation is attacked by a pi bond of phenyl acetate to place the tert-butyl group in the ortho, meta, or para position. The ortho and para pathways are electronically equivalent, but in this case the steric difference between the two is pronounced. So shown here, we see the attack of a pi bond on the tert-butyl carbocation, leading to the formation of the para-substituted sigma complex. This sigma complex has the expected 3 resonance forms in which the carbocation is continually delocalized to new locations on the ring. But in this reaction, for either ortho or para sigma complexes, one additional resonance form is possible, and that additional resonance form delocalizes the charge onto the carboxyl oxygen of the ester. This resonance form is especially stable because every atom in this resonance form possesses a complete octet. And this lowers the energy of the sigma complex for the ortho or para products, making them the most favorable in this particular reaction. The final step entails the loss of a proton from the sigma complex to chloride, which restores aromaticity to the ring and yields predominantly the para product for both steric and electronic reasons. If we briefly examine the meta pathway, we'll see why it is not favored in this particular reaction. Shown here is the formation of a meta-sigma complex. While the meta-sigma complex does have delocalization of the charge around the ring, there is no opportunity for the carboxyl oxygen of the ester to further delocalize the charge. Therefore, the resonance hybrid for the meta-sigma complex is higher in energy than the ortho and para-sigma complexes. Consequently, this pathway is not favorable in this particular reaction. In this next example, benzaldehyde is alkylated with 2-methyl, 2-butanol, and sulfuric acid. This is an unexpected reagent combination, but as we'll see shortly, it still generates a carbocation that can serve as the electrophile in this EAS reaction. Also notice that in this particular reaction, it is now the meta product that is formed predominantly. Protonation of the alcohol hydroxyl group is the first step of this mechanism. It affords an oxonium ion, and that oxonium ion is bonded to a tertiary center, which would make a reasonably stable carbocation, and therefore water dissociates to form that tertiary carbocation. This carbocation is no different than a carbocation formed from an alkyl chloride and aluminum trichloride. Consequently, it is equally suitable in a Friedel-Crafts alkylation. The subsequent attack of the aromatic ring could place the alkyl group in the ortho, meta, or para position. Let's examine the preferred meta pathway first. While the meta-sigma complex has only 3 resonance forms, notice that the carbocation is never placed on the center that is directly adjacent to the carbonyl carbon. This will become important when we compare this pathway to the ortho-para pathway. As we would expect, the reaction concludes when chloride dissociates from aluminum tetrachloride and removes a proton from the only sp3 hybridized ring carbon, thereby restoring aromaticity to the ring and providing the meta product. If we now turn our attention to the ortho-para pathway, we will see why it is not favored in this particular reaction. Shown here, we see the attack of a pi bond of the aromatic ring on the tertiary carbocation to generate a para-substituted sigma complex. This para-sigma complex also has 3 resonance forms that delocalize the charge around the ring. This is very similar at first glance to the meta-sigma complex. However, one of these resonance forms suffers from electrostatic repulsion because the carbocation is placed on the carbon that is directly adjacent to the partially positive carbonyl carbon. This raises the energy of this particular sigma complex, making it unfavorable. Since the ortho sigma complex is electronically equivalent to the para sigma complex, we expect both the ortho and para pathways to be disfavored for this particular reaction. A potentially surprising complication in the Friedel-Crafts alkylation is that primary alkyl chlorides other than methyl chloride or ethyl chloride result in rearrangement products. For instance, Friedel-Crafts alkylation of benzene with propyl chloride does not yield the expected propylbenzene. Instead, isopropylbenzene is formed as the product. Let's see why. The first step in explaining this result is the formation of the Lewis acid-base complex between propyl chloride and aluminum trichloride. There is significant partial positive character on the primary center. So much so, in fact, that it behaves as if it were a primary carbocation. That primary carbocation is shown here in quotes because it does not actually exist. But if we did have that primary carbocation, we would certainly expect it to undergo a 1,2 hydride shift to form the more stable secondary carbocation. An analogous process happens with the Lewis acid-base complex. Since there is so much partial positive character on that primary center that it behaves sort of like a primary carbocation, we see a 1,2 hydride shift, which happens to concurrently displace aluminum tetrachloride. And this results in the formation of the secondary isopropyl carbocation. And the sigma complex formed through the attack of the benzene ring on the electrophilic carbon attaches not a propyl group, but an isopropyl group to the ring. Loss of a proton to chloride restores aromaticity to the ring and completes the formation of isopropyl benzene. So notice that Friedel-Crafts alkylation of benzene with either isopropyl chloride or with propyl chloride yields the same product, isopropyl benzene. And we have now seen the mechanisms for both of these specific reactions in this presentation. The Friedel-Crafts alkylation has some limitations that you should be aware of. It does not work well with rings bearing nitro or amino groups. That's because nitro groups withdraw a great deal of electron density from the aromatic ring, making it too weak of a nucleophile for this reaction. Amino groups, on the other hand, are Lewis bases, so they will react with aluminum trichloride, resulting in an electron-poor ring that is also too weak of a nucleophile for this particular EAS reaction. The Friedel-Crafts alkylation has an additional limitation, and that is that the reaction is problematic with rings bearing carbonyls that are conjugated to the ring. These could be aldehydes, ketones, acids, amides, esters, or the similar nitriles. In any of these cases, aluminum trichloride would complex with a lone pair of these functional groups, and the resultant Lewis acid-base complex renders the aromatic ring too electron-poor to react. This is actually the reason that an alcohol and sulfuric acid were used as alternative reagents in the reaction with benzaldehyde shown earlier in this presentation. Alkyl groups, once installed on the aromatic ring, can be oxidized to the corresponding benzoic acid, provided that the benzylic center bears at least one hydrogen. The reaction requires potassium permanganate or sodium dichromate and sulfuric acid. Notice that any additional carbons are cleaved off of the benzylic center as the benzoic acid is formed. In summary, Friedel-Crafts alkylation is an EAS reaction that replaces a proton on an aromatic ring with an alkyl group. When secondary or tertiary alkyl chlorides are used, they are converted to carbocations by aluminum trichloride. And these carbocations are the potent electrophiles that are subsequently attacked by the aromatic ring. On the other hand, when primary alkyl chlorides are used, the Lewis acid-base complex itself serves as the potent electrophile for the EAS reaction. But it's important to remember that primary alkyl chlorides larger than ethyl chloride will rearrange, and this makes it generally impractical to install primary R groups containing 3 or more carbons via this reaction. Furthermore, when the reactant has a substituent on the ring, the relative stabilities of the sigma complexes determine whether orthopara or meta products will be favored. The preceding has been an excerpt from the book Introductory Organic Reaction Mechanisms, a color-coded approach to arrow pushing. If you found this video to be helpful, you may be interested in the complete book, which is available in ebook format from Scribd, in paperback from Amazon, or in paperback at a discounted price from Lulu.